In this portion of the textbook, I describe the results associated with some repeated random sampling from the population of 100,000 cases, which has a population mean of 7.31. And I have represented those results with mean 1 all the way to mean 10. And the sample sizes are heading each column. So sample size of 5, 10, 50, all the way to 5,000. And these were the first means I randomly sampled from the population, which again I randomly sampled with the SPSS program. This is the 100,000 cases, and I used the data select cases utility, and I randomly sampled 5 cases 10 times, and that's with replacement. So each time the program takes 5 cases, they're basically put back into the population and they can be reselected again for another sample. So I randomly sampled 10 times, and these are the means I obtained, the sample means I obtained for sample size of 5. And you can see that they're fairly variable around a population mean of 7.31. And the lowest mean here is 6.6. And the largest mean looks like an 8. And they're hovering around 7.31. But the grand mean, this GM, grand mean, is the average of these means. So I summed all these mean values and then I divided by 10 to get an average, if you will, a mean. We call a mean a grand mean, GM, in statistics. So that's a 7.24. And then I subtracted the grand mean from the population mean of 7.31. And in this case, as you can see, that gave 7.24 minus 7.31, negative 0.07. So that's the grand mean minus mu. That's how we pronounce the population mean from a statistical standpoint. Some people pronounce it mu. And the standard deviation, which is really important here, is literally the standard deviation associated with this collection of 10 means. And the standard deviation actually represents the standard error of the mean. So the standard error of the mean is the standard deviation of the means from a repeated sampling perspective. And in this case it equaled 0.51. We move up to a sample size of 10. The grand mean was 7.21 and the standard deviation of the means was 0.33. So that means that the standard error of the mean for these sample sizes of 10 is smaller than the standard error of the mean associated with just 5 cases. And that's what we expect. We expect there to be a smaller amount of variability in the sampled means as the sample size gets larger. Now if we move up to 100, we can see the standard deviation has dropped quite precipitously from the rather small sample size of 5 down to 100. And this is why I say in the textbook, doing analyses with 5 or 10 cases is not usually very useful. But once you get up to 50, 100, then you're in a position to make some results that are associated with a respectable level of confidence. And then finally, with a sample size of 5,000, the standard error of the mean is very small. Look how little variability there is in these sample means, which are all quote-unquote trying to capture that 7.31 population mean. They're doing it very closely. This one did it perfectly. But there is still some error, and that standard error is represented by the standard deviation associated with these means. So if you literally put these means into a program and calculated the standard deviation, you would get this value, 0.02, and that corresponds to the standard error of the mean. And in this case, the grand mean associated with these sample sizes of 5,000, which is very large, is very close to the population mean. 7.32 minus 7.31 gives 0.01. So that was the purpose of consolidating all these results in this table, was to present how the consistency in the estimation of the means changes quite drastically as we move from a very small sample size of 5 to 50, 100, 1,000, and 5,000. And that's where I suggested that a sample size of 5,000 is about as good as it gets in terms of the trade-off of spending more time and money to get more data and gaining more accuracy. It's really not a huge benefit. So it's a very minuscule benefit, really. So that's the representation of the standard error of the mean from the perspective of repeated sampling.